Welcome to today's class on vector analysis. Today we discuss constrained maxima and minima. Sometimes we need to find the extreme values of a function whose domain is constrained to lie within some particular subset of the plane, a disk, for example, or a closed rectangular region or along a curve, etc. So such type of problems are called problems of constrained maxima and minima. We will discuss a problem and we will discuss a more powerful method to find the extrema in such situations. So first we discuss a problem. This is done by substitution. Now this is an example of a problem of constrained extrema. Here we have to find the point px by z closest to the origin on the plane 2x plus y minus z minus 5 equal to 0. So the constraint here is the point lies on the plane 2x plus y minus z minus 5 equal to 0. So we'll solve this problem. So this is the situation. Now this is the plane 2x plus y minus z minus 5 equal to 0. So this plane. So our problem is to find the point on the plane such that distance from the point to the origin is minimum. So you consider a point here, you consider this distance, and you consider another point here, you consider this distance, etc. So you consider all the distances from origin to the plane and find the minimum of the distance. So that is our problem. So here the constraint is that the point lies on this plane. Solution. So the problem is that you consider all points P, X, Y, Z on the plane. So you consider P, X, Y, Z on the plane, and you suppose that this is origin O. So you consider this distance OP. OP. So our problem is to minimize OP. Here the constraint is that the point lies on the plane 2x plus y minus z minus 5 equal to 0. So solution. So let P, X, Y, Z be a point on the plane 2x plus y minus z minus 5 equal to 0. So we have to find point P on the plane such that OP is minimum. So we have OP is the distance from origin to XYZ. So it is equal to square root of x minus 0 the whole square plus y minus 0 the whole square plus z minus 0 the whole square. So that is square root of x square plus y square plus z square. So this is OP. Minimizing square root of x square plus y square plus z square is equivalent to minimizing x square plus y square plus z square. So our problem is to minimize f of xyz equal to x square plus y square plus z square subject to the constraint that xyz belongs to the plane 2x plus y minus z minus 5 equal to 0. Now since x, y, z belongs to 2x plus y minus z minus 5 equal to 0, we have z equal to 2x plus y minus 5. Therefore, we have to minimize h of xy, that is equal to f of x, y, z is 2x plus y minus 5. So that is equal to x square plus y square plus 2x plus y minus 5 the whole square. So this is equal to x square plus y square plus 4x square plus y square plus 25 plus 4xy minus 10y minus 20x. So this is equal to 5x square plus 2y square plus 4xy minus 10y minus 20x plus 25. Now we have the domain, so we have this is h of xy, and we have the domain of h of xy is the entire plane, entire xy plane. Therefore, by first derivative test, minimum occurs at critical points. We have hx is 10x plus 4y minus 20, and hy is 4y plus 4x minus 10. Therefore, hx equal to 0 implies 10x plus 4y minus 20 equal to 0, and hy equal to 0 implies 4y plus 4x minus 10 equal to 0. Therefore, 10x plus 4y equal to 20. So this is equation 1, and 4y plus 4x equal to 10. This is equation 2. Now we solve equation 1 and 2. So equation 2 implies x plus y equal to 10 by 4. So that is 5 by 2. Or this implies, so equation 2 implies x plus y equal to 10 by 4. That implies x plus y is equal to 5 by 2. So from this equation you are getting, this implies y is equal to 5 by 2 minus x. So you substitute y is equal to 5 by 2 minus x in equation 1. Therefore, equation 1 implies 10x plus 4 into 5 by 2 minus x equal to 20. So this implies 10x plus 10 minus 4x equal to 20. So this implies 6x is equal to 20 minus 10. So that implies 6x equal to 10, x equal to 10 by 6. So that is 5 by 3. So when x is equal to 5 by 3, you have y is 5 by 2 minus x. So 5 by 2 minus 5 by 3. So this is equal to 15 minus 10 divided by 6. So this is 5 by 6. Therefore, 5 by 3, 5 by 6 is a critical point of h of xy. Now we have to find z. So we have z equal to 2x plus y minus 5. So this implies z is equal to 2 into x is 5 by 3 plus y is 5 by 6 minus 5. So this is equal to 10 into 2 plus 5 minus 30 divided by 6. So this is equal to 20 plus 5 minus 30 divided by 6. So this is equal to 25 minus 30 divided by 6. So this is minus 5 by 6. Therefore, the point P x y z is x is 5 by 3, y is 5 by 6, and z is minus 5 by 6. So this is the nearest point to the origin on the plane, which is the point on the plane 2x plus y minus z minus 5 equal to 0, closest to the origin. And we have OP is square root of 5 by 3 the whole square plus 5 by 6 the whole square plus minus 5 by 6 the whole square. This is equal to square root of 25 by 9 plus 25 by 36 plus 25 by 36. So this is equal to square root of 25 into 6 plus 25 into 4 plus 25 plus 25 divided by 36. So this is equal to square root of 150 divided by 6. So this is approximately equal to 2.04. Therefore, the minimum distance from origin to the plane 2x plus y minus z minus 5 equal to 0 is approximately 2.04. You can illustrate this using GeoGebra. So this is your GeoGebra window. You first plot the plane. So 2x plus y minus z minus 5 equal to 0. Then you plot the point 5 by 3, 5 by 6 minus 5 by 6. And then you plot the point origin O. And you know that this is the point P and this is the point O. Now you consider the distance OP. You know that it is approximately equal to 2.04. So you consider the segment. This distance is your OP. So you can see the figure. So this is the closest point on the plane to the origin. And this distance is 2.04 approximately. So you can see that this distance OP is 2.04. The attempts to solve a constrained maximum or minimum problem by substitution, that is the method that we have used in the previous example, do not always go smoothly. So there are situations at which the substitution method fails. So we will illustrate this using following example, and that's why we are going to introduce a new method to find the constrained extremum. So that method is known as method of Lagrange multipliers that we will discuss in the next class. So now we discuss an example in which the substitution method fails while finding constrained maxima or minima. So consider this example. Here again we have to find the closest point to the origin on the hyperbolic cylinder x square minus z square minus 1 equal to 0. So the constraint here is the point lies on the hyperbolic cylinder x square minus z square minus 1 equal to 0. So solution, let P be a point on the hyperbolic cylinder x square minus z square minus 1 equal to 0. That is P x y z belongs to the hyperbolic cylinder x square minus z square minus 1 equal to 0. So you may consider this hyperbolic cylinder using GeoGebra. So you consider the hyperbolic cylinder x square minus z square minus 1 equal to 0. So this is the hyperbolic cylinder you have in this example. You have to find the point P on the hyperbolic cylinder x square minus z square minus 1 equal to 0 such that distance from origin to that point is minimum. So we have considered a point P on the hyperbolic cylinder and you have the origin O. So you have to minimize the distance between O and P. So you consider OP. So we have OP equal to square root of x square plus y square plus z square. And since xyz belongs to the hyperbolic cylinder, x square minus z square minus 1 equal to 0, we have z square equal to x square minus 1 and f of xyz is x square plus y square plus z square and h of xy is f of x y x square minus 1 because z square is x square minus 1. So this is equal to x square plus y square plus x square minus 1. So that is equal to 2x square plus y square minus 1. And since domain of h is the entire xy plane, we have extrema occurs at critical point. Therefore, by first derivative test, at critical points, hx equal to 0 and hy equal to 0. Now, since a domain of h of xy is entire xy plane, we have minimum occurs at critical points. Therefore, hx equal to 0 and hy equal to 0 implies we have hx is 4x and hy is 2x. Therefore, hx equal to 0 implies x equal to 0 and hy equal to 0 implies y equal to 0. We have z square equal to x square minus 1. So this implies z square equal to minus 1, and which is not possible. Since Z belongs to R, set of reals. You can observe that there are no points on the hyperbolic cylinder at which both x and y coordinates are 0. Both x and y coordinates are 0 means points on the Z axis. So there are no points on the Z axis which lies on the hyperbolic cylinder. So the method fails here. So this method of substitution is not valid always. So we may think about new methods. So we will introduce Lagrange multiplier theorem. And before that, let us see what has happened in this case. What happened was that the first derivative test found the point in the domain of h. You know that h is a function of x and y, where h has a minimum value. And on the other hand, we want points on the cylinder where h has a minimum value. And you know h of xy is defined over the entire plane. So although the domain of h is the entire plane, the domain from which we can select the first two coordinates of the points x, y, z on the cylinder is restricted to the shadow of the cylinder on the xy plane. That does not include the band between the lines x equal to minus 1 and x equal to 1. So you know that from this figure, you know that the domain of f is the portion of the plane which does not include this part, this band. And all the point except this band is the domain of definition of the cylinder. But the domain of definition of h, that is a function of two variables, was the entire plane. So that is why this method fails. So in such situations, we have to introduce a new method. So that we will discuss in next class.